In the last episode, we explored how to use AutoML in ML.NET to automatically find models that work well for our data. I mentioned that the next video would be feature engineering, but I think it's better to first talk about cross-validation. So today in episode 4, we're taking the next step, understanding cross-validation, one of the most important techniques to make sure your machine learning models are truly reliable. Instead of training on one big chunk and testing on another, we split the data into multiple small folds, train multiple models, and average the results. This gives us a much stronger and more realistic estimate of accuracy. In this episode, I'll show you exactly how cross-validation works in ML.NET, why you should use it, and how it makes your models more robust before you deploy anything into production. So let us dive in and improve the quality of our predictions. Now in the code editor in Visual Studio, let us start with cross-validation. As said in the previous videos, in the series I follow the comment first approach. So here I start with the comment and let Copilot write the code for me. It seems right. Yes, this is the method I expect cross-validate. And I choose number of faults 5. And here is the documentation of the method in .NET, the number of faults, and this method will create five sub-models. And will be trained against our label column, which is if any goals will be scored in the first half. Now we should output the metrics, and so we can decide if the metrics are good for us or good enough. We can use our training pipeline as our final model or our final pipeline. If the metrics are not good, we can change the trainer or the algorithm, and so on and so forth until we find an appropriate model that can we use in the production. So here are the steps just to output the metrics. Now we scroll back to the splitting code where we split the data in a training and test fractions. We don't need it for now. We just want to use cross-validation. And don't worry, at the end of the video, I will explain the cross-validation once more. So here I just delete the code from the previous videos about the manual evaluation and the AutoML code. And now we should just have the pipeline with cross-validation. Here is the context, loading the data, converting it to classification data where we defined our label column, the definition of the pipeline, the chosen trainer or algorithm, SGD calibrated, and here's the cross validation and the metrics. We will we will run the model and train it on the final data. This now is just for showcasing. Usually you output the metrics and you change or you evaluate different models, not only the SGD, but different models till you reach the desired metrics or the desired validations. But for now, we just have one model. Let us give it a try. Here we see the 5 faults for each, the accuracy, the AUC, and the F1 score. And also the average metrics. Accuracy is about 73, AUC is about 57, and F1 score is about 84. We have successfully applied cross-validation on our data. Now let us dive into the world of cross-validation, and to make the life easier for you and me, I decided to consult Copilot about cross-validation. And here is my question. In machine learning, I split the data, which makes the trained data more smaller. Um, Explain cross-validation. Cross-validation lets you use all available data for both training and validation by repeatedly splitting the data into different train validation folds. This was number 5 in the code. It gives a less noisy, less biased estimate of generalization than a single train test split. And why? We use it especially useful when your dataset is small. What is the problem with single train test split? A single split permanently removes the test portion from training, which can leave you with very little training data and a high variance estimate of performance. What to do after cross validation? Use cross validation to select model and hyperparameters. And this what you didn't see in the code. We just have had one algorithm, one trainer, and the metrics. So the next question would be how I use cross-validation and apply hyperparameters to select the model. This is a practical copy-pastable implementation that shows K-faults cross-validation for model selection, simple hyperparameter grid, multiple trainer options, and choosing the best pipeline by averaged CV metric AUC. You can choose another one, F1 score if you like. Then training the final model on all data. So, um, and here is the code. This is the pipeline. It's called here base pipeline. It's like our pipeline, but without the trainer. Therefore, uh, it's called base pipeline. So we have here the features, just the features, without an algorithm. The algorithms will be defined with different options and added to the list of candidate pipelines. So we have here two two options for the same algorithm, SDCR, with different options. Here is, for example, um, the maximum number of iterations is different. And we have here the algorithm fast tree with also two different options. Here are the number of faults 5, and here we iterate in the list of pipelines, and um, we in every iteration we compare the IUC with the previous AUC, and if it's better, we set it in the best variable. So let us give it a try. I copy this code from here and paste it in my code editor. As said, we don't set the algorithm here. So here is a pipeline without an algorithm. I pasted the code and I have some errors that's expected, and this is the base pipeline. Okay, I also delete my pipeline. Here is the base pipeline and without algorithm. I don't need the label because it's already set in my classification data. And here is the list. We have 4 options, 2 algorithms with 4 options, and here are the iteration. Okay, links, it's count. And here's one more. Okay, let us give it a try. Great. We used 5-fold cross-validation to evaluate multiple candidate pipelines, so every sample contributes to both training and validation. Candidates were ranked by mean AUC across faults. The top pipeline was retrained on the entire dataset to produce the final deployable model. Although 5-fold cross-validation and hyperparameter selection identified the best pipeline, the achieved AUC is not satisfactory, so we must explore other solutions. For example, feature engineering, richer models, or additional data. The immediate next step is focused feature engineering to extract stronger signal and reduce noise before further tuning or model changes. See you in the next video.